Good morning, good afternoon, good night, wherever you are. Welcome to Between Two North Show. We are having our esteemed guest, Dmitry Afanasiev. We are going to continue be talking about how to scale data centers, and we'll try to kind of start where we stopped last time. So without further ado, I'll bring in Dima. So please go ahead.
Hey, so let's continue more or less from the same place we finished last time, but well, in no particular order. Just as a recap, this is the kind of data center topologies we are building in our data centers. Pretty much what all the other hyperscalers and companies with big infrastructure are building. It's class or folded class. It's people in different places call it slightly different names. But anyway, it's 3 stages with 2 spine levels and 1 level which we call top of the rack. Some people are calling it leaf. Once again, there are some differences in terminology, but basically it's the same topology, the same structure. And most recent iteration in our case is we are building class with 8 planes. That means each top of the rack switch has 8 uplinks, and then we have like separate planes with spine 1 and spine 2 switches. Planes are not connected between each other, so each plane is completely separate and isolated entities. They only can see each other through top of the rack, basically. But they actually don't see each other because top of the rack just uses them as independent entities through which it can forward traffic. But that's just for recap. And what's interesting here is that this structure and data centers are physically large. That means when we are building data center, when we are trying to optimize it, we have to make some decision about what kind of links, kind of transceivers we are going to be using. Basically, we have to think about physical infrastructure because all those diagrams are good, and design and tracing routing is important, but eventually we have to do physical packaging. And what's interesting here is that basically it is physically large. That means we can't really avoid using long links. What we came up with in our situation is that there are 3 cabling segments, basically. One from the host to top of the rack, another one from top of the rack to spine 1, and then spine 1 to spine 2. And since entire data center is like hundreds of meters geographically, that means there are going to be some really long links that require optics, and most likely single mode optics. Then there is segment which is closer to hosts. It's between top of the racks and spine 1 switches, and we can do some optimization here. It's possible to use multi-mode optics or even active optical cables, because it's really like on the order of 100 feet or 30, 40 meters, something like that. And then once again, within a rack, we can use really cheap connectivity in the form of twin axial copper cables, because it's only 1 to maybe 3 meters. And that's the situation we have now. Looking into the near or midterm future, it looks like the distance we can go with multi-mode optics is going to shrink further. So probably instead of what we are doing now, like intermediate length segments with multi-mode optics and really long segments with single mode optics, probably they're going to be both single mode. Because for 800 gigs, multi-mode reachability is something on the order of dozens of meters. That's it. And also on high speeds, twin axial cable reachability is also shrinking, and some time ago there was some flexibility about how you can put switch within a rack and how you can arrange servers. Now we are moving to the situation where it's not really top of the rack switch, it's middle of the rack switch, because we have to optimize physical distance. And hopefully we can use that arrangement for some time, but eventually it looks like we will have to use optics even within racks, but not next year, not next couple of years. And also because of the structure of closed network, not only there are a lot of cables and need to manage different levels, there is a need to somewhat optimize complexity, because there are a lot of links, and when people do physical infrastructure, it's easier to work with not a lot of links where every link is unique. It's easy to work with like cable bundles, which go from the same, at least rack to the same rack, and have the same length and so on. So it's just a way to deal with complexity. What we do is we are using hierarchy. We are trying to factor out something to have a lot of, if we have a lot of items, at least we can try to have similar items and so on. And that's of course what we did. And well, there are a lot of things to unpack here, but like previous iteration of data center design, we used intermediate optical cross connects exactly to manage cable bundles. And it is rather complex, because there are two pictures here on the left side, and on the left side, it essentially describes connectivity between all the blocks within data centers, and those small squares, I'm not sure if it's visible, but hopefully it is, and you see a call out. Each small square is actually 64 by 64 links interconnect. So it's rather big. Doing optimization of how it's physically arranged is also important. And so that's how it looks in real life, not fully assembled, but like it's intermediate stage of data center deployment. You can see spine switch racks on the left, and optical cross connects on the right.
It's a beautiful picture.
I can keep it for a while if you want to. Yeah. Another interesting thing is that those things are like physically large, because the data center we are talking about, where these pictures are from, just spine 2, top of fabric level, it occupies 32 full racks. So it is big. I mean, when designing, we need to take into account how much space and cooling all those switches will occupy, and patch panels and cross connects. The space we need just for data center network is starting to be comparable with significant percentage of the space we are using for compute resources.
Dima, when you design physical placement of super spine or T2 switches, do you place them in a couple of different groups in different rooms, different power supplies, or you place them in a single row? What's the idea here with placement?
In our case, they place it even in separate, it's the same kind of building, but in different rooms. It's not what, for example, Google or Facebook is doing, if I remember correctly, but it's because we are not only limited by things like physics, like power and cooling and airflow and so on. There are also regulations, and that's related how all the fire extinguishing things and are regulated, and whether people can enter a particular room or not. So we were limited by some other factors, and because of that, we are not using like single big open space data center. It's split into several sections with walls between them, and there are also separate rooms where we keep things like external connectivity, like edge routers, optics, I mean long-range optics, DWDM, and also top of fabric. That's also because how we do cooling, because we have we are doing like free space cooling, and even in cold corridor, the temperature can be as high as 35 degrees centigrade. That's how we design our servers, because we use custom design for servers and service rack. But that's unfortunately not the same. The environment big switches are optimized for. And that's another reason to keep those big boxes, a lot of those big boxes in a separate room, which has better air conditioning.
And
also,
to reiterate, it's very similar to how all other large data center provider design it. At Microsoft, we've got 4 different locations, which we call ADF, where we place T2 or super spines that are responsible for every plane.
Yeah, because if it's only like 1 or 2 switches in the rack, it's probably feasible to keep them in the same environment, more or less. But if it's really a lot of high-density boxes and switches are not particularly good for airflow, because the entire front plate is basically occupied by transceivers, you don't have enough space for air to flow through, so they really need somewhat better cooling than typical server. I mean, even if power density is the same, in network equipment, front plate is unfortunately mostly blocked. So yeah, there is a need to have better cooling environment for those boxes.
Yeah, and actually decouple to reduce phase sharing between different planes. So if one goes down or into maintenance, you can, to some degree, ensure that other planes are still working and active.
Yeah, and so actually, we're not only keeping it in the separate room from like most of the compute infrastructures. There are 2 such rooms which are physically separate by like 100 meters or so. So they're attached to different parts of the common data center structure, and they of course have redundant power feeds. That means that optics also come in not exactly the same point. So wide area optic lines, they're coming to different points in the building. That means like single backhaul probably cannot bring all the optics down, only half of it. At least
while we
not
are
very
talking
fast.
about the hierarchy, let's touch upon routing and complexity. Could you describe in some details what do you advertise down, what do you advertise up, whether you summarize role of default routes, and whether you do something more intelligent than ECMP, for example, weighted ECMP?
Yeah, let's proceed with that. So that's the next slide, actually. I don't think we need to go through the discussion between link state versus path vector and so on, because that was already discussed on the podcast, and I guess
We had
most
Tony
of the
P
audience
for
is
4
familiar with that.
podcasts here talking about this in great details.
Yes, and also Petro Opohov, I guess.
Yeah.
So we are trying to keep things like as simple as possible. That means we are not doing aggregation. Idea is like following. We have on the order of 3 to 4K top of the rack switches. What we are trying to optimize is we are trying to optimize number of prefixes per switch. And at the moment, it's up to 4. There are some ideas about how it can be reduced further, but that means there are not that many prefixes in the data center, so less than 16K, let's say in our case. And it's not that many, and that's prefixes. From the point of view of any particular switch, most of those prefixes are behind the same set of next hops. Of course, we test for that scale, but we feel comfortable to go with such design because, well, if we are talking about modern merchant silicon, longest prefix match tables are usually quite good. We are talking about more than 100K entries in any decent chipset, not only now, but even a few years ago. What is really limiting us are other resources, which are ECMP groups and ECMP next hop entries, and I'm going to talk about that on the next few slides. So an aggregation because we discussed that and decided that we feel comfortable with the number of prefixes we have, and we don't want to introduce additional complexity because if we keep like canonical clause, all the planes separate, null side links, and so on, we can easily achieve desired prefix propagation in the BGP using just autonomous system arrangement. Basically, every top of the rack switch has its own IS number. All the spine 1 switches within a block have the same IS number. They share the same IS number. And then entire top of fabric shares the same IS number. And that means that announcements can only propagate the way we want them. Because if top of the rack switch advertise some prefix, it can go up to the spine 1 level, and it can then propagate to all the other top of the rack switches, but they cannot once again propagate it back because it's going to go through the same group of spine 1 switches. That means the same IS number, so now it's not going that way. And the same goes for the next level. So basically, announcement can propagate all the way up, and it can change direction one time. So it can go to the spine 1 level and then propagate it down to top of the rack. So it can go all the way to top of the fabric level and then propagate down. But it cannot change direction second time. And that's what we want. It's value-free, not routing, it's value-free announce propagation.
And we covered this in podcast 1, 2, 5, 4, and 6. It's very important to have this strict propagation scheme to avoid path hunting and really explosion of tables. And potentially we might discuss if you would want to, why you might want to change it, especially if you use something like lossless RDMA classes, but maybe for another podcast.
Yeah, I guess so. Yeah. So we feel comfortable with that. And our problem is that aggregation is a good way to work with and to solve routing system scaling problems. But basically, when we have aggregation and we have ECMP, there is a danger that we are going to arrive at a point where aggregate announcements came from, but there is now path from that point down to actual destination. And once again, if I remember correctly, Piotr talked about that and how they deal with that in Facebook design.
So they actually bonds ones up to have backup longer paths available. And they market
yes, so if you from particular span you cannot go to particular top of the rack switch, you can go through some other or load share or all the other top of the rack switches which will bounce through other spines and so on. So yeah, it's going to work. It's adding 2 hops, but generally it's going to work. But it makes routing system more complex. And we feel that if we can avoid that routing system complexity, we probably are going to keep it the way we do. Two remarks here is that why we can keep the number of prefixes per switch is really low is that we are using IPv6. So we can allocate large prefixes and we don't need to manage them dynamically. And that's internal infrastructure where we control entire stack, both network applications, libraries, TCP/IP stack tweaks, some filtering. I mean, we have software components like host-based firewalls and so on. So we control everything. We can allocate large prefixes. Those prefixes are stable and they're coupled to topology, so they're not moving between racks and switches. And in different environments, something like public cloud, there are customer prefixes which are very dynamic. They can move from point to point, and they are not aggregated even on switch level. The way to do that is to use overlays, and that's what all the cloud providers are now doing. That's a way to decouple addressing and routing in the underlay and in the overlay, and to achieve underlay scalability.
Question to you, and potentially very interesting for our listeners. So when we started to deploy IPv6 in data centers, maybe 5-6 years ago, we figured that advertising /128 reduced capacity to store this route significantly because most of the switching silicon is optimized towards /64, right? So which led in a lot of cases to implementation of kind of local aggregation where you have /128, but you advertise /64. Did you have to do this, or you can advertise actually /128?
Are you using that for loopbacks or?
Yeah.
We are keeping 128, and for next hops, so for links between switches, we are just using link locals.
Okay. So it's an important consideration because if you are deploying today, I still remember early tests like in 2013 where you would get one number with /64 or shorter prefix and suddenly half of it with /128. I believe by now all modern silicon programming IPv6 prefixes independently of prefix lengths or with very insignificant difference. So if you deploy it today, probably you don't need to dance around it. You can just advertise longer prefixes as Dima describing.
Yeah, and as I said, if we are talking about longest prefix match tables, it's on the order of 100K and more. So in our case, we were comfortable that we have some forwarding table space to spare. Even if those entries are taking twice as much space, so it's still not a big problem.
Could you please say a few words about aggregation as you go up? Do you actually aggregate data center ranges when you go towards one or regional network? Where do you do aggregation in general?
We do. So of course, what I described is what we do inside data centers, but data center itself present to the rest of the infrastructure, I mean to the other data centers, to wider networks, is a number of aggregated prefixes, of course. And it's hosts in other data centers, they are not mostly interested in those aggregated prefixes, even they're usually interested in virtual IPs, because services are usually represented by some load balancing infrastructure. You don't want to go to a particular host. You usually want to get service.
So would be correct assumption that you filter out, just aggregate somewhere at superspine or perhaps one layer higher and advertise on the default routes towards hosts?
Sorry?
Would it be correct assumption to kind of describe it that what goes down towards Tor is mostly default routes for destinations that are outside of data center.
Yeah. They're getting like default routes to get outside. They're getting some virtual IPs, and that's it. And hosts don't really need large, like anything beyond default, because we are using single-homed hosts.
So the interesting question here, normally you would aggregate data center into hopefully few large blocks and advertise them upstream. What if you use anycast services across data centers? In this case, they're not aggregatable, right? It has to be more specific route, so you go to the best anycast IP destination from perspective of routing device.
You mean using anycast inside data center or
Yes.
outside data?
Inside.
Inside, yeah. Trying to really avoid that. I mean, really, service endpoints are some virtual IPs, and it's possible to do anycast inside data centers, but it introduces not really like mock. It's not complex to do anycast. What's complex is to do a really good distribution of queries and so on, and also you need to keep things in mind, like if there are some faults and TCP/IP flow hashing changes, you're probably going to arrive to different anycast destination and so on. So it really depends on the problem we are trying to solve and what the point is. If it's stateless or stateful. For stateful services, we probably really don't want to use at least naive anycast implementations. And also on the host side, infrastructure is changing. That also depends on what particular system we are talking about, because if it's like a MapReduce cluster or something like that, hosts are talking, agents and hosts are talking with cluster management nodes, and they can get particular destination with not anycast but specific address. If it's some other services, they're probably getting to load balancing infrastructure and routed to some particular destination host and so on. So a solution is different for applications.
Makes sense. Thank you. So next question with regards to weighted ECMP. Have you considered using it? Are you, and pros, cons from your perspective?
We considered using it some time ago, but decided not to proceed at that moment, mostly because vendor support was hit and miss. It was several years ago. So once again, it just was going to introduce more complexity than we wanted to have, and much more testing because features were not really ready in the software. And we are using door vendor policies, or in any particular data center, there are going to be at least two different vendors. That means two routing stacks. There are benefits in case one vendor is bringing some really nasty bug, but that means also that sometimes we have to wait longer to get some new features. So it wasn't just ready for prime time at that moment, and also there is a problem with weight granularity, and for that, we need to discuss how ECMP forwarding is really implemented in modern chipsets. So,
yeah, which is probably great segue.
I should have like a couple of slides,
okay,
but I need to skip something.
I don't want to interrupt your flow, so please go ahead and.
Actually, it's a good question, and but we really need to discuss how ECMP forwarding and equal and weighted ECMP can be implemented. So what we have, and it's slightly simplified pictures. There are slightly different implementation, but like average high-speed modern chipset, when we are doing forwarding and ECMP or weighted multipass forwarding, how things go. First, we have longest prefix match lookup, and as a result, we are getting either next hop if it's a single pass, or we are getting pointer to ECMP group. And ECMP group essentially consists of pointer to the ECMP next hop or adjacent table, and also a number of entries. And then we calculate hash from packet headers, trim it, or doing model division, so the result is not larger than the number of next hops in the group, and add it to the base, to the index in the next hop table, which we got from a particular ECMP group, and that's how we find our next hop. And usually, if you're talking about modern chipsets, the number of ECMP groups would be something on the order of 4K. And the number of next hops and adjacencies, it's something from, let's say, 16K up to 32, maybe 64K, but I'm not even sure about last one. It's usually where our resources can be shared. The size of groups is usually limited, so a particular group can be, once again, it's not universal, but that's how many chipsets are designed, that you can have like standard size groups, and it's usually up to 32 or 64 entries per group. And there could be a few very large groups with something like 1K entries in the group. But if you have 16 or 32K entries at all, and group is 1K entries, that means you only can have 32 groups or 16 groups, which is not. So most of the groups are going to be small. And in a small group, you have a group, and for example, there are 32 entries. And by the way, the size of like a standard size group it's usually half number of interfaces per switch, which makes sense. If you go in one direction, it's probably not going to use more than half of the interfaces. And in close without option, it's like half interfaces up, half down. So it's long, and it's what we see on many chips. So if it's 64 port switch, group is probably limited to 32 entries. On 128 port switches, it's usually up to 64. On some more advanced, more feature-rich platforms like feature-rich routers, it could be better, but if you're talking about switches, it's like that. And for example, forwarding is going, when we forward packets, it's going to through all those stages. And how weighted multipass is implemented is that we just have not single, but several entries with the same next hop for particular group. And that means that if the group is 32 entries, granularity is 1/32 of traffic, or 1/64 of the traffic going to particular destination. Basically, granularity is not good. For example, let's say we are sitting at top of the rack switch, and we have 8 uplinks. One of them goes down, or capacity is going down is actually not that complex. It's still ECMP, just a small number of links. Capacity is reduced. So how are we going to tweak it? We can, for example, have group with 32 entries, use four identical entries for some next hops and 2, 3 for other next hops. So on the third level, it sort of might work in some situation. But if we are talking about spine 1, exactly half links or on the order of half links are uplinks, and that's where ECMP goes. Now, good way to arrange weighted multipaths, because we are already using group with 32 entries, 1 entry per next hop. If you are having 2 entries for some particular next hop, it's going to get twice as much traffic as others. So granularity is really coarse, and it's not good. Some very recent chipsets are implementing something like more flexible. I haven't seen the description of how it's implemented physically. On the gate level, but have some ideas about that. But it cannot have entries basically, and then coefficient how much traffic goes to that particular next hop. So if the number of next hop entries per group is decoupled from the amount of traffic going to particular next hop, then yes, weighted multipath makes sense. But it's very recent, and a few years ago we couldn't really do that.
So I'll add some information on top of that. There's ongoing work in ETF, in TS working group. It's an informational draft really describing implementation where so-called DMZ community is not anymore per hop. It gets automatically accumulated and propagated. So it's very convenient where you just need to configure it, and then almost automatically transit switches will accumulate all next hops with this particular weight and propagate them down. So this is very convenient. On at least on Broadcom Silicon, SDK allows you to provide resolution. This goes exactly to what Dima described. You don't want number of next hop to be the same as number of weights. So, I mean, it's on SDK level. Vendors or most vendors have exposed knobs to change the resolution. So you might say that your array is 32 wide, but it will have only, for example, 4 different weight packets, right? So you reduce amount of data. You could go as granular as number of next hops. However, if you run out of resources, you can actually reduce it and obviously make load sharing less granular.
If I remember correctly, Tomahawk 4, for example, can implement like really fine-grained weighted load balancing. And not sure about how it's really implemented, but one way to do that would be, I haven't seen the documentation, so I don't really know, but what would be logical is, for example, for each next hop entry have a lower threshold and higher threshold, calculate hash function, and if it fits between those 2 thresholds, you use that particular next hop entry. If not, you go for the next and so on. So it's not really difficult to implement, but it cannot be backported to all the chipsets, so we probably need newer chipset. And this problem is better solved on the control point side, where we have problem right now is when we calculate something, we propagate weights, accumulate them, but when we try to install it into the actual forwarding tables, we have to deal with granularity of particular forwarding table implementation.
Yes, so to summarize this discussion, or at least discussion on weight CMP, now it's actually pretty much for the first time, there are solid implementations on all commercial vendors plus FRR. So they all support DMZ community as well as proper propagation of such. As if you remember, it's non-transitive. It had been defined in draft as non-transitive, and now we are updating this behavior to become transitive. So you don't really need to violate ITF specs. So chipsets would allow you, so anything, as we said, Tomahawk 4, Trident 3 does it really well. So if your capacity upstream is limited and you would like to attach some more information than just next hop to default you advertise down, potentially now it's a good time to rethink your strategy. And for example, if you have, 4, 8, or 16 ways up, you might attach weighted community to every default route. And when you go into maintenance or this particular group goes down, you will reshuffle traffic according to weights. It's a complex solution, but if you get it right, it could work really well for you.
Yeah, and I want to add that if you are going to have more advanced, more interesting topologies and closing data centers, something like Dragonfly Plus or whatever, basically, or expander graph basis, whatever. We really will need proper weighted ECMP with fine granularity. It's not going to be ECMP, weighted multipass and even pass with different lengths, but what would be needed as well is fine-grained balancing between those paths.
Yeah.
And do I have a few minutes, to continue discussion about ECMP?
Yeah, so let's continue and finalize discussion on ECMP and kind of finish there and continue in 2 weeks.
Yeah, since we are talking about ECMP, I want to talk a little bit about MPLS and ECMP. At one point, we really wanted to do data center design with MPLS, and there are a lot of arguments for it. Well, not like standard MPLS with all the complexities of traditional MPLS control point stack, but more something like lightweight segment routing with label stacks coming from some sort of controller. But anyway, what was the problem and why it was we eventually have to discard that idea, at least for a while? If you are talking about IP, CMP, several prefixes can share the same ECMP next hop group. But if you are using labels, at least like vanilla MPLS implementation, then groups cannot be shared because we rewrite labels. So we do label lookup. It points to ECMP group. Group once again has index, count, whatever, but what's inside that each next hop entry is, it's not only MAC address for the neighbor and interface we are forwarding through, but there is also a label rewrite information. And since each label could be written into a different value, we have to allocate a block of next hop entries and separate the ECMP group for each label. And this doesn't scale because if we are having 8K, 16K destinations, each one has its label. That means we need the same number of ECMP groups and so several thousands of ECMP groups. And then we need to multiply that by number of next hop in each group, which is, for example, on spine 1 switches, ECMP is the biggest problem on spine 1 in our case. Or basically, if somebody is building a closed network with more than 2 spine levels, ECMP is going to be the biggest problem on all the spines except for the topmost spine, because top of the rack switches usually have not that many uplinks, and top of fabric, the last spine level only have downlinks, but everything in between usually have very wide ECMP. So going back to MPLS, it doesn't scale in this implementation. Moreover, if we are talking about segment routing like architecture, then label rewrite is really, it's sort of dummy operation because we rewrite to the same value. But once again, unfortunately, all the chipsets couldn't really implement operation which is like get packet, lookup label, and rewrite to the same value. And
Define
use
the
the single.
continue in the IETF document.
Sorry?
Defined as continue rather than
Yes. Yes. So yeah, there is definition in ATF, but it's a result of more recent work for segment routing. It wasn't there for base MPLS architecture, if I remember correctly, and it wasn't really implemented in most chipsets, except for more recent one with some programmability where it's possible to describe such an operation. So it's not about the result of the operation. The result is the same. It's about how many entries and resources you are going to use to implement it. So externally observed behavior is the same, but amount of resources used in the silicon for forwarding is different. So really, if you want to use segment routing with MPLS data plane in the environment with a lot of alternative paths, we really need optimizations for continued operation.
So do you feel it's a good point in time to stop before we move to other topics?
We can, or I can talk a little bit about how to manage exit traffic, but probably it's a good point to finish today because there will be logically separate blocks to discuss later.
Yeah, indeed. So I would like to thank you again for coming up, and it's really great discussion and hopefully very useful people thinking of refreshing or maybe redesigning their data centers. And please do ask questions. We are going to be here in 2 weeks again with Dima and hopefully Jeff should be available, and we will continue this very exciting discussion. Thank you, everyone. Thanks, Dima. Thanks, support team. And we will see you in 2 weeks.
Thank you, everyone.